Hello, welcome. Let's try to solve another Leetcode problem. 2584. Split the array to make Coprime products. Let me first explain the problem and then try to find a method to solve it. But before that, let's check the nums I. It's going to be 10 to the power of 6. And the length of the array is 10 to the power of 4. So this is very important for us to solve the problem. So let's first try to understand what is coprime. The coprime is defined as GCD. So if the GCD of two values, value 1 and value 2 equal to 1, that means the value 1 and value 2 are coprime. Let's just use another example. Maybe let's just use 4 and 7. They are coprime because the GCD of 4 and 7 is 1. But we cannot solve this directly because the number is going to be really big. We cannot use a big number times a big number because definitely it's going to be time limit exceeded. Because the length of the nums array is 10 to the power of 4. If you can use a prefix or suffix array, and then you're going to need to use the number times the number. And the maximum number can be 10 to the power of 6. It means 10 to the power of 6. 10 to the power of 6 times 10 to the power times 10 to the power of how many numbers? Basically this number gonna be really big. So for each of the number 10 to the power of 6 and times 10 to the power of 6, and how many such numbers? And there's 10 to the power of 4 such numbers. It means 10 to the power of 6 times 10 to the power of 4. As you can see, this is going to be a really big number. Definitely it is impossible for us to use this way because even two numbers it's going to be 10 to the power of 12. If there are more numbers, if they're 10 to the power of 4 numbers, it's going to be 6 times 10 to the power of 4. So 10 to the power of 6 times 10 to the power of 4. So this number going to be really big. So for the computer cannot deal with such big numbers. Now this means we're going to use some other ways to solve it. So if we cannot use the GCD directly, so why not we just use the prime factors? So the idea for the prime factors is that for two numbers, so let me just use an example. For two numbers, so for example 4 and 12, we don't need to check the GCD directly. Because if the numbers is really big, basically we cannot use GCD, and we cannot even get the big numbers. But for the smaller numbers from the beginning, we just get the prime factors first, and we're gonna accumulate all the prime factors. So for example, we're gonna compare 4 and 12. So what is the prime factors for this 4? So I'm gonna put it inside a dictionary. So it means I'm gonna have a prime factor of 2. So basically I'm gonna have two prime factors, 2 and 2. So I'm gonna have this is gonna be a dictionary. This is my k. For number 2 I have 2 times. And what about 12? So 12 equals 3 times 4. So for the prime number 2 I have 2 times, and for the prime number 3 I have 1 time. So this means for this number 4 and number 12 I have the common prime factor. It is this number 2. If I have the common prime factor, definitely my GCD is not equal to 1. If the GCD is not equal to 1, it means it is not my result. So if the GCD equals to 1, this means I've already found the result. For example, 4 and 7. So this is a 2 and 2, and for the 7 I have 7 and 1 for the prime factors. So for this 2 and 7, there's no common numbers between. There's no common prime factors between 2 and 7. So for this 2 and 2 we have the common factors 2, but for this 2 and 7 we don't have it. If I check all the combinations and I didn't find one, I mean while I'm loop through the array, basically it is a prefix. This is 10 to the power of 4 time, 10 to the power of 4 time, and then I'm gonna check each one. And if inside the dictionary, if each of the numbers there's no common factors, basically this means I've already found it, so I'm gonna return I. If I didn't find it, I'm gonna return -1. So while I'm loop through the dictionary, so I'm gonna prepare two dictionary. One is the pre-dictionary. Yeah, so one is for the plain dictionary and one is for the suffix dictionary. I'm gonna use two dictionaries to check because that's gonna be all one time. If I were to check this number 2, if it is in another dictionary, it's gonna be just all one time. Yeah. So if all the numbers in nums in the pre-dictionary 1, this is a pre-dictionary 1, not in pre-dictionary 2, it means I've already found the index, so I'm gonna return the index. If I didn't find it, so I'm gonna return a -1. Yeah, I'm not sure if this is clear, but let's try to write the code because basically this is a mathematical problem. Definitely, we're gonna use some examples to explain it. Yeah. So the first step gonna be check the prime factors. So I'm gonna write it outside. So this is for acytosis E prime factors. Yeah, basically a lot of formulas you need to remember. Otherwise, how can you solve the mathematical problem? Yeah. So inside, I'm gonna put a number n. So in this way, I just use one time to check all the prime factors. For example, for number 8, I have the prime factors 2, 2, 2, and for 15, I have the prime factors with 3 and 5. So basically, in this way, I can find all my prime factors just use the function outside of my main class. This means basically I don't need to consider the time complexity in this area. Basically, this time complexity just runs in one time. It is 10 to the power of 6 times log 10 to the power of 6. It's gonna be a small value, basically 10 to the power of 7, but it should be okay. But after that, I will not consider the time complexity from here because this is written outside of the class, and I just needed to get the values. So the values is the divisors. Yeah, so if you are familiar with it, definitely this is a template for calculating the all the prime factors inside a dictionary with list. Yeah. So now it's gonna be totally the same as the acytosis prime factors. So yeah, let me just prepare primes. So the primes gonna be false. So this means from 0 and 1, it's gonna be false. Yeah. So false times 2, and from 2, it's gonna be true. Yeah. So true times n minus 1. Yeah. So the range is just from 0 to n, and this n is also inclusive. This is why I put it here, n minus 1 here with 2. It means this n is also inclusive. But for this n, it's for checking the prime factors for the range from 0 to n. This n is also inclusive. Yeah. Now I'm gonna check the I. I'm gonna check the with I from 2 to n plus 1. Yeah, because definitely 2 will be a prime factor, so it's gonna be the same. If you are familiar with it, if primes I, it means 2 is my prime factor. Then I use the acytosis save. I can save all the prime factors. Yeah. If this is true, and I'm gonna use another for loop. So for j in range I to n plus 1 to I. So here has to be this I, and the jump and the step gonna be I, and here is not with I times I because this is not the same. I times I is for the acytosis prime factors, but for this prime numbers, yeah. But we are calculating the prime factors, so we don't need to use I times I. It's gonna directly be I to n plus 1. Yeah, this means all the numbers, and the step gonna be I. Yeah. And then we need to put it inside the divisors. So the divisors. Yeah. So the divisors j gonna be append my prime factor prime factor gonna be I, because this I gonna always be the prime factors. Yeah, because I set it to be a true from the number 2. Yeah. Now I put it all inside, and I need to set it to be false. And yeah, because I put it inside, so for this number, for this index j, I need to set it to false. Basically, this means for this number j, it can be 2, because I've already put 2 inside, so I set it to false. And then I put number 4 inside, so this number 4 gonna be false. So this is just the acytosis prime factors method. So for example, 2, 4, 6. Yeah, if I choose all these numbers, basically I need to just delete it. So I need to set it to be a false. Yeah. So if you finish this area, basically you finished the most part of the problem. Yeah. Now let's just try to check what it looks like. So E prime factors, I'm gonna put 10 to the power of 6. Now let's just print out the dividers. Let's check if our function is okay or not. Basically, this is a template. Yeah, here let me just return 0. Let's just check. Return a -1. Let's just check if everything is okay. Yeah, I clicked wrong. Let me just check the. Yeah, let me just. Yeah, I wanted to check something, but it's okay. Yeah, let's just check this one. So for the number 2, we have a prime factor of 2. For number 4, we have prime factor 2, and for 6, we have prime factor 2, 3, and for 8, we have prime factor with 2. So this is okay. Yeah, and for 10, we have the unique prime factors 2 and 5. For 12, we have 2, 2, 3. So basically, it's gonna be 2, 3. And for 14, it's 2, 7, and 16, it's gonna be always 2, and 18, it's gonna be 2, 3, because 18 equals to 2 times 9, 2 times 3 times 3. So we just keep a 3. So this is gonna be all the unique prime factors for each number. Yeah, basically this is the first step. I think I explained it wrong. I explained we're gonna put all the prime factors inside. Actually, it is not. I only put the unique prime factors inside. Yeah. So this is gonna be the first step. Yeah. If we finish the first step, let's just try to continue. Now we finish the first step. We get all the prime factors for each of the number. Now I want to use a dictionary. I want to define a pre-dictionary. Let me just define a dictionary first. It's gonna be a default dict, and inside it's gonna be integer. And I want to loop through. All the numbers, and I want to put all the prime factors inside a dictionary, because I want to check all of them. Basically, this is a suffix dictionary. I will prepare 2 dictionaries. This is gonna be a suffix dictionary. I need to put all the numbers inside. So for n in nums, and then I can use another for loop. So for number inside dividers, I want to get all the dividers with this number n, and I want to put it in my suffix dictionary. So in this dictionary, I'm gonna take this number and gonna plus equal to 1. Yeah. And currently, I finished my suffix dictionary. Now I just want to check the prefix dictionary. Yeah. Let me just define a prefix dictionary. From the beginning, it's gonna be empty default dict, and it's gonna be empty. But I set it to be integer. Yeah. Now I'm gonna loop through all of them. Let's just try to check. So for in enumerate with the nums, yeah, and for each number inside the dividers n, yeah. So first, let's just check the pre-dictionary. So the pre-dictionary with this number gonna plus equal to 1. Yeah. But for this number, we're gonna need to check the suffix dictionary. The suffix dictionary need to minus this number. So for the suffix dictionary with the same number, we're gonna minus 1. Yeah. Now we need to check the suffix dictionary because it's minus 1. So we need to check if this one suffix dictionary equal to 0. We need to pop it. We need to pop out the k because it's equal to 0. Because later on we're gonna check if a number is inside the dictionary. So basically we need to pop it out. So yeah. So for the suffix dictionary, need to pop out the k, pop out this number because it's equal to 0. Definitely we're gonna delete it. Yeah. So we're gonna pop it up, pop out the number. Yeah. Now what we need to do, we need to have a final tag. So I'm gonna use O to tag. So if O, my value for value not inside. Yeah, so for this way is inside the prefix. It's inside the prefix dictionary. Yeah, so v not inside the suffix dictionary. For v inside the prefix dictionary, if all the values inside the prefix dictionary, not inside the suffix dictionary, definitely it means I've already found the index, so I'm gonna return AI. Maybe this is gonna be the difficult part. Let me just explain it. Yeah. So for the suffix dictionary, basically we're gonna let me first explain the prefix dictionary. Definitely we're gonna some prime factors. Maybe 2 have numbers of 2. It doesn't matter. At least I have them. Yeah. Maybe 3 have a number of 3. This is gonna be the prime factors. This is the prefix dictionary. But for the suffix dictionary, maybe I don't have 2 and 3. Maybe for 5, I have 1 time. For 7, I have 2 times. Yeah. So this means while we are checking this 2, it is not inside. And also, while we are checking this 3, it is not inside because there are 5 and 7. Definitely, if all of them not inside, it means the GCD of them equal to 1 because I don't have the common prime factor. Yeah. So this means it's going to be 1. So I'm going to return I. Yeah. But for my tag, I enumerate all the index. Yeah, but for the description, I should not do that. So this means I can only enumerate to the index 4, 0 to 4, as you can see, 0, 1, 2, 3, 4. I cannot enumerate this index 5. So this means I need to have a tag. Yeah. So from here, I can check it. So if I equal to length of the nums minus 1, it means I should not do that. Yeah. It means I didn't return anything I get here. If I get here, definitely I'm gonna return minus 1. Yeah, this means I didn't find it because this I equal to the end of length of nums minus 1. Basically, I don't need that. Yeah, it means from before I didn't find it, so I'm gonna return a minus 1. So this is gonna be the total function and total code for this problem. Normally, if you are familiar with this e prime factors function, acytosis to save the prime factors, this is going to be very efficient. You just need to copy the code directly, and from here you just need to write your code. Yeah, I'm not sure. Let's just try to run it to check. Yeah, as you can see, now it works. And why it works? Let's analyze the time complexity. Yeah, let me just submit it first, and then analyze the time complexity maybe. Yeah, as you can see, it works and it's pretty fast. I think it's 1.5 seconds. It is okay, but basically it's 86%. Yeah, 87%. Let's analyze the time complexity. Why it works? Because for here, as you can see, this is on time. N is 10 to the power of 4, and for here we used another for loop. But for this number inside of the divisors, because we are checking the all the unique divisors. So while we are checking all those unique divisors, this means this is just a log n time. Basically, it is even less than log n time. Maybe it is a log 10 to the power of 6. Yeah. If this is a log 10 to the power of 6, basically it's like 20. It means 10 to the power of 4 times 20. Basically, it is okay. 2 times 10 to the power of 5, it is okay. And for here, for this one, this is also like a log n time. Yeah, maybe you think, so for this way not inside the dictionary, this just takes 1 time. Yeah. But basically, we're gonna check this O function. We're gonna check how many values. Yeah. So this means for each value inside another dictionary, we just need to check all the prime factors. It means what is the length of the prime factors. It means m plus n. Yeah. And this m and this n is also the log of 10 to the power of 6. It's not definitely it's not a big number. Yeah, because we are just getting all the prime factors inside of this dictionary, and there should not be too many prime factors from 1 to 10 to the power of 6. Yeah, basically maybe it is just 100, just 100 or so, but definitely there will not be so many prime factors. 100 times 10 to the power of 4, so it should be okay for this problem. Yeah. So I think that's for it. Thank you for watching. See you next time.